Hi all, welcome to the YouTube channel C with series of digital electronics video course. So in this video, we will learn module 38 about the priority encoder. And in this video, we will cover the following topics. So in the module 37 video, we learned about the encoder. And we have also seen some limitations of this encoder. So the first limitation is, when more than one inputs of the encoder are high, then we will get the invariant output. And the second is when all the inputs of the encoder are 0, then we will get the same output when this D0 input is high. That means for the two different input conditions, we will get the same output. So these two issues can be resolved with the help of the priority encoder. So in the previous video, we briefly discussed about the priority encoder. But in this video, we will understand it in detail. And for that, first of all, let us start with the 4-to-2 encoder. So this 4-to-2 priority encoder has 4 inputs and 2 outputs. Working, truth table, and logic circuit. And 4-to-2 priority encoder, this one more output represents the valid input. So when all the inputs to the encoder are 0, then this V output is equal to 0. And when this V output is 0, then it doesn't matter what is the output of this A and B. So by sensing this V output, we can know the condition when all the inputs are 0. And when at least one or more than one inputs are high, then this output V will become 1. So when this V output is high, then the output A and B represents the valid output. So since it is the priority encoder, so each input has assigned the priority. And typically, the input with the higher subscript has the higher priority. So in this case, this D3 has the higher priority while this D0 has the least priority. So when only one input is high, then much like the normal encoder, we will get the output corresponding to that input. For example, when only this D1 input is high, then the corresponding output is equal to 0, 1. But when more than one inputs are high, then the input with the higher priority will be considered. And we will get the output corresponding to that input. For example, if both D1 and D2 are high simultaneously, then the D2 will have the more priority. And therefore we get the output corresponding to D2, that is equal to 1, 0. Or when this D1, D2 and D3 all are high, then the input D3 will have more priority. And therefore, we get the output corresponding to this D3, that is equal to 1, 1. So that is the working of this priority encoder. And here is the truth table of this 4-line to 2-line priority encoder. So as you can see, when all the inputs are 0, then the output V is also equal to 0. And at that time, it doesn't matter what is the value of this A and B. Now when this D0 is 1 and rest of the inputs are 0, then the output is equal to 0, 0. And since at least one input is high, so this V output is also equal to high. Similarly, when this D1 is high and this D2 and D3 are low, then the output is equal to 0, 1. And since the D1 has the higher priority compared to D0, so at that time it doesn't matter whether this D0 is high or low. That means whenever this D1 is 1 and these D2 and D3 are 0, then even if this D0 is 1, then also the output will be equal to 0, 1. Likewise, when this D2 is 1 and D3 is 0, then the corresponding output is equal to 1, 0. And since the D2 has the higher priority compared to D0 and D1, so at that time it doesn't matter what is the value of this D0 and D1. And lastly, when this D3 is 1, then the output is equal to 1, 1. And since the D3 has the highest priority, so at that time it doesn't matter what is the value of this D0, D1 and D2. That means whenever this D3 is 1, then other inputs can be either 0 or 1, but still the output will remain 1, 1. So that is the truth table of this 4-line to 2-line priority encoder. And with the help of the truth table, we can easily design the logic circuit of this priority encoder. So let us see that. So first, let us see this output V. So this output V is low, when all the inputs are low, and it is equal to high when at least one or more inputs are high. That means this V output is high when either D0 is high, or D1 is high, or D2 is high, or D3 is high. So this is the logic expression of this V. Similarly, let us see the logical expression of this A. So this output A is high when this D3 is high or this D3 is 0 and D2 is high. That means this A is equal to this D3 or D3 foot D2. Now here, using the distributive law, we can further simplify this expression. So as per the distributive law, this X or X invert Y is equal to X or X invert and X or Y. Now this X or X invert is equal to 1. So eventually, we will get this X or Y. That means this X or X invert Y is equal to X or Y. So similarly over here, this D3 or D3 invert and D2 is equivalent to this D3 or D3 invert and D3 or D2. And that is equal to this D3 or D2. So that is the expression of the A. Likewise, let us find the expression of this B. So as you can see, this B output is high when this D3 is high, or when this D3 and D2 are low, and this D1 is high. That means the output B is equal to D3, or D3 invert, and D2 invert, and D1. So once again, using the distributive law, we can further simplify this expression. So here, let's say this D2 invert and D1 is equal to X. That means this B is equal to this D3, or D3 invert and X. And once again, using the distributive law, we can say that that is equal to D3 or X, which is equal to this D3, or D2 invert, and D1. So that is the simplified expression of the B. So in this way, we got the three different expressions for A, B, and V. And with the help of these logical expressions, we can easily design the logic circuit. So, this is the logic circuit of this 4-line to 2-line priority encoder. So as you can see, using the two OR gates, this output V and the output A are generated. And using the AND, OR and the NOT gate, this output B is generated. So in this way, we can design this 4-line to 2-line priority encoder. Similarly, let's see this 8-line to 3-line priority encoder. Working, truth table, and logic circuit. So in case of this 8-line to 3-line encoder, 8 to 3 priority encoder, we have 8 inputs and 3 outputs. And to sense the condition when all the inputs are 0, we have one more output. So its working is very similar to the 4-line to 2-line priority encoder, but in this case, we have the 8 inputs. So here is the truth table of this 8-line to 3-line priority encoder. So as you can see, when all the inputs are 0, then this output V is equal to 0. And in this condition, it doesn't matter what is the value of this output A, B and C. Likewise, when this D0 is 1 and the rest of the inputs are 0, then the corresponding output is equal to 0, 0, 0. And since at least one input is high, so this output V is also equal to high. Likewise, when this D1 is 1, and the inputs from the D2 to D7 are 0, then the corresponding output is equal to 0, 0, 1. And since the D1 has the higher priority compared to D0, so it doesn't matter whether this D0 is 1 or 0. And likewise, we have different cases for D2, D3 up to D7. So based on this truth table, we can also find the logic circuit of this priority encoder. So first, let us find the expression of this output A. So if you want to skip this portion, then you can directly go to the next chapter. Alright, so this output A is high for the 4 different input combinations. That is when D7 is high, or when this D7 is 0 and D6 is high, or when this D6 and D7 both are 0 and this D5 is high, or when this D5, D6 and D7 is low and this D4 is high. So this is the logical expression of this output A. And once again, using the distributive law, we can further simplify this expression. So as we have seen earlier, this x or x invert y is equal to x or y. So similarly over here, we will try to minimize this expression. So if you see over here, then in the last three expressions, this D7 invert is common. So if we take it outside, then we will have this D7, or D7 invert, D6, or D6 invert, and D5, or D6 invert, and D5 invert, and D4. So let us say, this entire term is equal to x. So using the distributive law we can say that is equal to this D7 or x. And in this case, we can write it as this D7, or D6, or D6 invert, D5 or D6 invert, and D5 invert, and D4. So once again now if you see these last two terms, then here this D6 foot is common. So if you take it outside, then we can write it as this D7, or D6, or D6 invert, and in the bracket, we will have this D5, or D5 invert, and D4. So once again, using the distributive law, this D5, or D5 invert, and D4 can be written as this D5, or D4. And let's say that is equal to y. That means we will have this D7, or D6, or D6 invert, and y. So once again, using the distributive law, we can write it as this D7, or D6, or y. And that is equal to this D7, or D6, or D5, or D4. That means the output A is equivalent to this D7, or D6, or D5, or D4. And that is the simplified expression of the output A. Likewise, let us find the expression for the B. So as you can see, this output B is high when either D7 is high, or this D7 is low and D6 is high, or this D4, D5, D6, D7 is low and this D3 is high, or this D7, D6, D5, D4 and D3 are low and this D2 is high. So this is the Boolean expression of the output B. So once again, let's try to simplify it. So once again, in the last three terms, this D7 invert is common. So, let's take it outside and let's say, the remaining term is equal to x. So, in that case, we can write it as this D7, or D7 foot, x, and that is equivalent to this D7, or x. That means B is equal to this D7, or D6, or D6 invert, and D5 invert, and D4 invert, and D3, or D6 invert, and D5 invert, and D4 invert, and D3 invert, and D2. So once again, this D6 invert is common in the last two terms. So, let us take it outside, and let's say, the remaining term is equal to y. That means we can write it as this D7, or D6, or D6 foot dot y. And that is equal to this D7, or D6, or y. Where this y is the remaining terms, after taking this D6 invert outside. So now, we will have this D7, or D6, or D5 invert, and D4 invert, and D3, or D5 invert, and D4 invert, and D3 invert, and D2. So once again, in the last two terms, this D5 invert and D4 invert is common. So if we take it outside, then we will have this D7, or D6, or D5 invert, and D4 invert, and in the bracket, we will have this D3, or D3 invert, and D2, which is equivalent to D3, or D2. So overall, if we see the minimized expression, then that is equal to this D7, or D6, or D5 invert, and D4 invert, and in the bracket, we will have this D3, or D2. So that is the overall minimized expression of this output B. And likewise, let us also see the expression for the C. So this C output is high when this D7 is high, or this D7 and D6 is low and this D5 is high, or when this D4, D5, D6, D7 is low and this D3 is high, or when this D7, D6, D5, D4, D3 and D2 is low and this D1 is high. So this is the logical expression of the output C. So once again, let's try to simplify it. So as you can see, in the last three terms this D7 invert is common. So let us take it outside, and as we have seen earlier, as per the distributive law this D7 invert will get eliminated. Moreover, in this last three terms, this D6 invert is also common. So let's also take it outside. So now, we will have this D7, or D6 invert, D5, or D5 invert, and D4 invert, and D3, or D5 invert, and D4 invert, and D3 invert, and D2 and D1. So once again, in the bracket, if you see, then in the last two terms this D5 invert is common. So, let us take it outside. And let's say, the remaining term is equal to y. So now, we will have this D7 or D6 invert, and in the bracket this D5 or D5 invert and y. So once again, using the distributive law, we can write it as this D7 or D6 foot, and in the bracket this D5 or y, which is equivalent to this D4 invert and D3 or D4 invert and D3 invert and D2 invert and D1. So this is the simplified expression of the output C. So in this way, we got the three expressions of the output A, B and C. So lastly let us see the expression of the output V. So this output V is equal to 0 when all the inputs are 0. And it is high when at least one or more inputs are high. So this is the logical expression of the output V. So in this way, we got the logical expression of the output A, B, C and V. And based on these expressions, we can easily design the logic circuit of the encoder. So let's make the logic circuit of the same and let us run the simulation. Simulation of 8 to 3 priority encoder. So as per the four equations which you've seen, this is the logic circuit of this 8 to 3 priority encoder. So let me just run the simulation, and let me show you the output result. So as you can see, when all the inputs are 0, then this output V is also equal to 0. And whenever any of the one input will become 1, then this output V will also become 1. So here, let me just make this D3 input as 1. So as you can see, as soon as I made this D3 input as 1, this output V also becomes 1. And in that case, if you see this output A, B and C, then they are 0, 1, 1, which corresponds to the input D3. Now at the same time, suppose this D5 input is also high, then we will get the output corresponding to D5, because here this D5 has the higher priority. So as you can see in this case, this corresponding output is equal to 1, 0, 1. And at the same time, suppose this D7 is also high, then we will get the output corresponding to D7, because this D7 has the higher priority compared to the D5. So as you can see, in this case, our corresponding output is equal to 1, 1, 1. So in this way, this circuit will work as the 8 to 3 priority encoder. Alright, so now let us see how to design this 8 to 3 priority encoder using the 4 to 8 to 3 priority encoder using 4 to 2 priority encoders, 2 priority encoders. That means suppose, if we do not have this 8 to 3 priority encoder, then how it can be implemented with the help of the 4 to 2 priority encoders. So, as we have seen, this 8 to 3 priority encoder has the 8 inputs. And since we are implementing it with the help of the 4 to 2 priority encoders, so we require 2 such encoders, so that we can apply the 8 different inputs. So here the inputs D0 to D3 are applied to the first priority encoder, while the other inputs, that is from D4 to D7, are applied to the second encoder. And once we apply these inputs, then we also require the additional circuit to use it as the 8 to 3 encoder. So let us see that. So, here is the truth table of this 8 to 3 priority encoder. So if you see over here, then this output A is equal to high when either D4, D5, D6 or D7 is high. And other than that, this output A is equal to 0. So basically, when any of the input of the second encoder is high, then this output A is equal to high. So we can get that signal with the help of the V2. So as we have seen earlier, this output V is high when any of the input is high. That means in the second priority encoder, this V2 will be high when any of the input between D4 and D7 is high. So in this case, this output V2 represents the output A. Similarly, let us see this B output. So this B output is high when either D2 or D3 is high, or when this D6 or D7 is high. So this D2 and D3 are the third and the fourth input of this first encoder. Likewise, this D6 and D7 are also third and fourth input of this second encoder. So if you see the truth table of this 4-to-2 encoder, then when this third input is high, then the corresponding output is equal to 1, 0. And when this fourth input is high, then the corresponding output is equal to 1, 1. So in both the cases, this A input is high. So at the first glance, it appears that, just by performing the OR operation of this A1 and A2, we will get our output B for this 8-to-3 encoder. But actually, that is not the case. Let us see why. So let's say, this input D2 and D5 are high simultaneously. So as per the truth table of this 8-to-3 priority encoder, this D5 has the higher priority. So when both the inputs are high, then we should get the output corresponding to D5. And that is equal to 1, 0, 1. That means when this D5 input is high, then this output B will remain 0. So if we just perform the OR operation of this A1 and A2, then in that case this B output will remain high. And in that case, this circuit will not work as the 8-to-3 priority encoder. So we need to ensure that, when any of the input of the second priority encoder is higher than the first priority encoder, should get disabled. Or in other words, the output of this first priority encoder should get disabled. And for that, we need to know that when any of the input of the second priority encoder is high. So we can know that with the help of the output V2. So as I said earlier, when this V2 is high, it means that at least one of the input of the second parity encoder is high. That means whenever this V2 is high, then this A1 and B1 should get disabled. And therefore, by performing the AND operation of this A1 with the V2 invert, we can disable this output. For example, when this V2 is high, then this V2 invert is low, and therefore, this output of the AND gate will become low. So in this way, by performing the AND operation of this A1 and B1 with this V2 invert, these two outputs can be disabled when any of the input of the second priority encoder is high. That means to generate this output B, we should perform the OR operation of this AND gate with the A2 right. Well, still we have one more issue, and that might occur when all the inputs of the second priority encoder are 0. So now, let's see the second case, when all the inputs of the second encoder are 0, and the inputs of only this first encoder are high. So in that case, as per the truth table, when all the inputs of the second encoder are 0, then this V output will become 0. And in that case, we don't care what is the value of this outputs A and B. That means whenever this D4 to D7 are 0, then of course this V2 is equal to 0, but at that time this A2 and B2 can be anything. So when all these inputs are 0, then this A2 and B2 should not affect our overall output. And to ensure that, we should disable this output A2 and B2. So we can do that by performing the AND operation of this A2 and B2 with the V2. So when this V2 is 0, or when all the inputs of the second encoder are 0, then the output of these two AND gates will become 0. And since they are disabled, so it will not affect the overall result. So now, to generate this output B, we can perform the OR operation of these two AND gates. So basically, these two AND gates represents the outputs A1 and A2 with the disabled inputs. Similarly, by performing the OR operation of these two AND gates, we will get our C output. So basically, these two AND gates represents the outputs B1 and B2. So let us also see that with the help of the truth table. So as per the truth table, this C is high when either D1 or D3 is high, or when this D5 or D7 is high. So these four inputs represents the second or the fourth input of this 4-to-2 encoder. So for these two inputs, if we see the corresponding output of this encoder, then they are either 0, 1, or 1, 1. That means in both the cases, the output is high. That means somehow we need to perform the OR operation of this B1 and B2. But like I said before, we just directly cannot perform the OR operation of these two outputs. And that is why we require the two more AND gates over here. So just by doing the OR operation of these two AND gates, we will get our desired C output. And at the end, to get all the 0 input condition, we just need to perform the OR operation of this V1 and V2. So when all the inputs are 0, then this V1 and V2 both are 0, and by sensing the output of this OR gate, we can know that when all the inputs to this encoder are 0. So in this way, we can design this 8-to-3 encoder using the 4-to-2 encoders. Simulation result. So now, let me show you the simulation result for the same. So this is the circuit of this 8-to-3 priority encoder using the 4-to-2 priority encoders. So here, the circuit which is shown in this green color represents the 4-to-2 priority encoder. So as you can see, this output V2 represents the output A, and here, this output A1 and A2 are logically ORed with the help of the AND gates. And similarly, to get this output C, this B1 and B2 outputs are logically ORed with the help of the AND gates. So this AND gates will ensure that we will get the proper output of this priority encoder. So now let me just run the simulation, and let me show you the output result. So as you can see, when all the inputs from D0 to D7 are low, then this output V is also equal to 0, and if I make any of the input as 1, then this output V will also become 1. So here, I am making this input D1 as 1. So as you can see, as soon as I make this D1 input as 1, then this output V will also become 1. And moreover, if you see these outputs A, B and C, then they are 0, 0, 1, which corresponds to the output D1. Now suppose at the same time, if this D3 input is also 1, then the corresponding output is equal to 0, 1, 1, because this D3 has the more priority compared to D1. On the other end, simultaneously, if this D5 input is also high, then we will get the output corresponding to D5, because this D5 has the more priority compared to this D1 and D3. So in that case, the corresponding output is equal to 1, 0, 1. And suppose at the same time, if D7 is also high, then we will get the output corresponding to D7. Because this D7 has the highest priority among all inputs. So as you can see, when this D1, D3, and D5 and D7 all are high simultaneously, then we will get the output corresponding to D7, that is equal to 1, 1, 1. And whenever all the inputs are 0, at that time, this output V is also equal to 0. So in this way, we can design this 8-to-3 priority encoder using the 4-to-2 priority encoders. So I hope through the simulation results, you got the idea how we can design these priority encoders. But you can also use some directly available encoder ICs. For example, this IC74148 is also 8-to-3 priority encoder. And it can be directly used for some applications. But this IC has the active low inputs and outputs. So while using this IC, you need to keep that thing in mind. So if required, then I will also make the separate video on this IC. But right now, I am including the datasheet of the same IC in the description. So for more information you can check that link. So that's it for this video, and I hope in this video, you understood the working and the design of this priority encoder. So, if you have any question or suggestion, then do let me know here in the comment section below. If you like this video, hit the like button and subscribe the channel for more such videos.